Good morning, all of you.
Morning, doctor.
Can we start now? Is my screen visible?
Yes, doctor.
Okay, thank you. Okay, so yesterday we have introduced this topic Z transform, which is similar to the Laplace transform. Actually, Laplace transform we do in the continuous time domain. The Z transform is for the discrete time systems. Okay, so the important thing we have seen about the Z transform is the region of convergence, where h of z should not be equal to infinity, it should not get infinity. So we have seen how to find the region of convergence for the given sequence, and then we have seen the uh, two important properties like causality and the stability. Okay, so the causal system, how to find the causality of the system using Z transform with the region of convergence, that also we have seen. So basically the system or the sequence or the signal can be a causal, non-causal or anti-causal. So the system is causal when h of n equal to 0 for negative n. The system and we'll get the ROC right-handed ROC we will get like this. For the anticausal system, that means h of n is 0 for n equal to 0 and the positive values of n. So the ROC for that system is the left-handed, that is inside this circle. And for the non-causal system, we will get the ring type structure. Okay. So today, and we have seen some problems on that. Now today, basically, we will focus on the stability, how to find the stability of the system. Okay. Now, for a stable system, basically, this is the definition that the say stable system unit circle must be inside the ROC. Okay, so in this picture, you can see that these are the different ROC structure. Now, here, unit circle is also plotted in the Z plane. Okay, now in the first case, which is the right-sided ROC, that is exterior ROC also you can say. So you can see if this alpha that is inside circle is having, if it is less than 1, then the unit circle will include in the ROC. So we can say that this system is stable. Okay. Now this is the left side ROC. Just a second. Okay. Now in this picture you can see this is the left sided ROC. Okay. Or you can say interior ROC. Now if this alpha is greater than 1, then unit circle will be inside this ROC. Then this type of system will be stable. Now, if we are having the ring structure, so there is inner circle which is alpha and the outer circle is beta. Okay, and in between, if this unit circle exists, then in that case, this system is stable. Okay. So this is the definition of the uh, stability. Now again, we can also find the stability using the location of the pole and zeros. Okay. Now, in this case, how to define the poles and zeros of the system? Now, basically this Z transform is in the form of polynomial, the ratio of the polynomial. That is h of z, I can say this h of z is p of z divided by q of z. Okay. This p of z is the polynomial in the z inverse or in z form, and q of z is also a polynomial in terms of z or z inverse. Okay. Now, how to define this poles and zeros of the system? Okay. Now, the poles and zeros of the system can be defined like this. Zeros are the values of z that causes this h of z equal to 0. Okay. Zeros are the values of z that causes h of z equal to 0. Okay. Which causes h of z equal to 0 if your numerator is 0. Correct? If your numerator is 0, then this h of z will be 0. Therefore, the values of 0 is can be find out when you make this numerator part equal to 0. Okay. Now, the poles are the values of z that causes h of z equal to infinity. Which causes h of z equal to infinity if you make q of z, that is denominator part, is equal to 0. Okay. So the zeros, the poles can be find out using this denominator part. Okay. If we make this denominator equal to 0, then we'll get h of z equal to infinity. Okay. Now this h of z is in the form like this. Okay, this is numerator and denominator. Okay, so h of z is basically, in the previous examples also we have seen that we'll get this type of polynomial. This is the ratio of polynomial we'll get. Okay, now the ratio of the polynomial in terms of z inverse. Most of the time we write in terms of z inverse. Okay, because we are having the standard formula using z inverse, like alpha z inverse to the power n. Okay, so for that we know that the uh, h of z is 1 minus 1 minus alpha into z inverse, like this. So we write the polynomial in terms of z inverse. Okay, so in general case we can write this numerator part, this part, like the summation of the product of this. Uh, if this is the polynomial till power minus m, then this we can write like this product, like z minus some beta 1, z minus some beta 2 till z minus some beta m, and this capital M. Okay, so this is basically the product of z minus beta m. Okay, if you do the multiplication till m equal to small m will goes from 1 to capital M. So this many zeros will be there. Capital M zeros will be there. Okay, why we are writing like this? Because we need to find the location of zeros. So this polynomial expression we will solve in this term. Okay, similarly, this denominator polynomial we can express like this: z minus alpha 1, z minus alpha 2 till z minus alpha capital N. Okay, so that this alpha 1, alpha 2, this alpha n are the poles. Okay, this beta 1, beta 2 till beta m are the zeros of the system. Okay, so if we make this equal to 0, numerator equal to 0, then we'll get the zeros. If we make the denominator part equal to 0, then we'll get the poles of the system. Okay, so in general, we write this denominator part in this form. Okay, this is product of this over n equal to 1 to capital N. So this capital N zero poles will be there in the system. Okay, so this B of M is basically are the zeros. This beta of N are the zeros. Alpha of N are the poles of the system. Okay, so we will uh, do this with one example. So this example we have already seen. So if we are having the impulse response like this, alpha to the power n u of n. So we know that the Z transform of this. So how to find the Z transform of this? So u of n, basically the summation will go from 0 to infinity instead of minus infinity to infinity. Okay. So alpha to the power n into Z to the power minus n. Apply the Z transform formula. So what you will get here? You will get 1 divided by 1 minus alpha Z inverse. So yesterday we have also seen the region of convergence for that. Okay. Now look into the poles and zeros of this system. Okay. Look into this expression, how to find zeros and poles of the system. Now in this case, what we have done, so for the easier calculation, what we have done, so we are having the polynomial in terms of Z inverse. Okay, so we will express this in terms of Z. So we write this h of Z instead of Z inverse polynomial. We will solve this and we will write this in terms of Z. Okay, so if you take Z inverse common in the denominator, then this is Z minus alpha and the Z inverse goes in the numerator. So we will get Z divided by Z minus infinity, Z minus alpha. Now to find zeros, we need to make numerator, need to equate this numerator to 0. So therefore, there is only Z, one Z. Okay, the power of polynomial is only 1. Therefore, we will be having only one 0. And that 0 is at Z equal to 0. Okay, now to find the poles of the system, we need to make the denominator equal to 0. Okay, and this polynomial is having power 1, therefore only one pole will exist, and that pole is at what? This pole is at Z equal to alpha. Okay, now the poles and 0, there is a symbol how to represent poles and 0 in the Z plane. So zeros will represent with this circle, small circle representation, and poles like this cross symbol. Okay, so like this we need to draw poles and zeros in this Z plane. Okay, now here you can see we are having 0 at Z equal to 0 at this origin, and the pole at alpha. Okay, therefore it is shown like this. This cross and this is 0. This is pole and this is 0. Okay, now we know that the region of convergence for this. If we make this term less than 0, if we make mod of z inverse less than 0, then this will not goes to infinity. H of z will not go to infinity. So the region of conversion is basically if mod of z is greater than alpha. So we will get the right sided ROC or exterior ROC. So this is will get the ROC like this okay, exterior of this alpha. Now how to find the stability of the system? If the unit circle exists here in the ROC region, then only our system will be stable. Okay, or we can say that if this alpha is less than 1, in that case our system will be stable. Okay, the definition of stability using Z transform is this. If the unit circle exists in the ROC, then only our system will be stable. Okay, so in the discrete LTS system, basically how we say the stability. So we say that the system is stable if and only if the impulse response is absolutely summable or the square summable. This is we say in terms of the discrete times. In general statement, the stability we say like this: if it is absolutely summable or the square summable, then our system is stable. Okay, so this stability basically we find with using the impulse response of the system. Okay, so using the Z transform, in Z transform, what we are doing, we write this Z in terms of this R e to the power j omega, or we make the signal like suppose I'm having signal x of n. So we write this like x of n to the power minus n. So this term is actually absolutely summable. We make this term absolutely summable. Now, in case of the Z transform, if our ROC exists this unit circle, then only we say that the system is stable. Okay. Now, here, while calculating the stability, okay, now we find the stability using the impulse response, that is h of n. Okay. Now, if I'm having the h of n, then the Z transform of this impulse response is h of z, and this is also known as the term, there is one term called transfer function. Okay, the Z transform of this impulse response h of n is also known as the transfer function. Okay, this is the transfer function of the system. Okay, and we say that the system, the discrete time linear time invariant system, is stable if the transfer function, that is h of z, has a region of convergence which includes the unit circle. Okay, so basically transfer function we write in terms of the polynomial of zeros and poles. Okay, so we say that zeros when the transfer function is equal to 0, and poles is when the transfer function is equal to infinity. Okay, so basically we write this, we have seen this is in terms of polynomial p of z by q of z. Okay, so p and q are the polynomial in z or z inverse, you can say. Okay, so the roots of this denominator is called as a poles. The roots of the numerator is called as the zeros. So we find the roots using this polynomial, numerator and denominator. So if we represent this polynomial in this pattern, then it can be easily find out the roots of the polynomial. Correct? Now, so we say that the roots, the place where the transfer function is infinite, then these are the poles and of the system, and basically for the stability poles are very important. Basically for the poles determine the stability of the system, or poles determine the region of convergence of the system. Please understand, the poles determines the region of convergence or the stability of the system. Okay, so zeros are not that much important here, but the location of pole is very important in this case. Okay, as long as the all the poles lie strictly inside the unit circle, then the region of convergence will include the unit circle and the system will be stable. Okay, so this is very important in terms of the stability. Okay, now from this example we know that we are having pole at this alpha. Okay, so this pole basically uh, determine the region of convergence. So the region of convergence will start from this, and this is the exterior of the this circle or with radius alpha. Okay, there is one more thing which is very important. Region of convergence will not include zero, the poles. Okay, no poles will be included in the region of convergence. Okay, now we will see one another example here. So suppose we are having impulse response like this. So I'm having h of n equal to delta of n minus 3 delta n minus 1 plus 2 delta n minus 2. Have you understood these terms, zeros, poles of the system? Yes, students? Is there any doubt? Is this okay?
Everything good.
Okay. Now, suppose h of n is like this. This is the delta function. Okay. Now for this, delta is only exist at n equal to 0. If I'm having this delayed delta, delta n minus 1, so this delta will exist at n equal to 1. Okay, please understand this thing. Delta will exist at n equal to 0. So the value of is equal to 1 at n equal to 0. For this delta n minus 1, this will exist at only n equal to 1. For this, it will exist only at n equal to 2. Okay, so we know the delta function in discrete form. So the delta function we write like this. Okay, so it is having value at n equal to 0. Correct? So this is delta of n. Delta of n minus 1 is at n equal to 1. I am having value 1. Okay, similarly for n equal delta n minus 2. So find h of z for this n of h of n. Okay, so we apply the formula of z transform. So z transform is what? Summation from minus infinity to infinity. This is our h of n into z to the power minus n. Okay, now separate all this term. So multiply z to the power minus n to each term. So we will get this. Okay, now this is only exist at n equal to 0. So I can directly write this is 1. The magnitude is 1 at n equal to 0. Therefore, this is z to the power 0 first term. Okay. Minus this will exist only at n equal to 1. Therefore, this magnitude is 1. So 3 into 1, and this is z to the power minus 1. Similarly, this term 2 into 1 for n equal to 2. Therefore, z to the power minus 2. Okay. Now, this is equal to what? This is equal to z to the power 0 is 1 minus 3z to the power minus 1 plus 2z to the power minus 2. Now, if we take z to the power minus 2 common here, so we will get this polynomial here, z square minus 3z plus 2. Okay, and then z to the power minus 2 we can write directly in the denominator. Okay, now this polynomial is of the power 2. So we will get z minus beta 1, z minus beta 2. So we write this polynomial z square minus 3z plus 2 like this. So this is the value of beta 1 is 1 if you find this, and this is 2. Okay, so this we have written like this. Now find the location of pole and zeros for this. So zeros can be find out when the numerator is 0. Okay, so z at z equal to 1 and z equal to 2, zeros will exist. So there are two zeros in the system. Okay, at 1 and 2. This is our entire z plane. Okay, now at this 1 and 2, zeros will exist. Therefore, you need to denote here in the z plane with this circle. Notation is circle. What about the pole? So poles, then when we make the denominator equal to 0, then we can find out the poles, which makes transfer function infinity. Okay, so pole, there again the polynomial is in the power of 2. So there are two poles, but at what location? Z equal to 0. This is z square only. So we are having two poles at z equal to 0. So this is represented with this and 2 is written here. Okay, that means we are having two poles at this origin. Okay, now how to find the region of convergence for this? So basically region of convergence is uh, we can find with the location of pole. Okay, so the region of convergence for this is the exterior of the origin. Okay, so it will start from this because the poles are at the origin. Okay, except origin, entire z plane is the region of convergence. Okay, therefore we can say that in the region of convergence, unit circle will exist and the system is stable. Okay, the system is stable here. Okay, Now, these are the characteristics of the ROC, region of conversion. The boundary of ROC is a circle centered at Z for the above example. Okay, at Z equal to 0. This is the boundary of the ROC, entire Z plane except at origin Z equal to 0. Now, this is very important thing. Only poles will determine the ROC. Zeros gives no effect to the ROC. This is very important. Okay. The ROC is a region between poles, thus there must be no pole inside ROC. Inside ROC, there should not be any pole. Okay. ROC region can be between the poles. Like if I am having this, suppose I'm having the poles at this two location, and this is suppose my ROC. Okay. These are two poles. So there should not be any third pole between this ROC. Okay. So this is also very important. ROC is the region between the poles and there must be no poles inside ROC. Okay. ROC is a connected region. This is also very important. Okay. So ROC is a connected region and there are only three shapes of ROC are valid. Okay. So which three shapes like this? So these three shapes are valid for the region of convergence. Otherwise, there will be no ROC. Okay. So this is the left-sided ROC, which is exterior ROC or outer ROC, you can say. This is inner ROC. This is right-sided. This is left-sided ROC. And this is ring type ROC. Okay. So these three ROCs are valid. Otherwise, there will be no ROC. Okay. So the outer ROC is basically the right-sided signal. And we know that for the causal system, we will get this type of ROC. Then the system will be causal. Okay, the signal will be causal. The inner ROC is the left-sided signal. And for this, the system or the signal will be anti-causal signal. Okay. The ring type ROC is the non-causal system, which is the combination of both the exterior and interior. Therefore, we will get the rings type structure here. Okay, which is also called as a two-sided signal. Or for the two-sided signal, we'll get the ring type structure. Okay, so two-sided signal means the signal will exist or h of n is exist for negative n as well as the positive n. Okay, that is the two-sided signal. Okay, so right-sided signal means what? This will exist for positive n. Left-sided signal means h of n exists for the negative n. Two-sided signal means this is exist for positive as well as negative n. Okay. For finite length signal, ROC is the entire Z plane except Z equal to 0 or Z equal to infinity or both. Okay, we have seen yesterday the example on this. If ROC is inclusive of the unit circle, then the system is stable and the Fourier transform for this LTI system exists. Okay, so these are the important characteristics of this ROC. Okay, so this is about the stability. Is there any doubt regarding the stability of the system? Yes, student.
I guess there is no
Okay, so we will see some properties of the Z transform. Write the slide here. Properties are also important. So we know the standard property linearity. Okay, so linearity property is, so the Z transform of alpha x1 n plus beta small x, I write x2 n is equal to alpha x1z plus beta x2z. Okay, so the Z transform, this is the linearity property of the Z transform, like we have seen in the DFT DTFT. Further property is time shifting. So time shifting means Z transform of x of n plus m. The Z transform of this is equal to z to the power m x of z. Okay, this is the time shifting property of this. If we represent this with this is okay, I guess. Then the third property is the differentiation. Z transform of n times x of n is basically equal to minus z d by dz of capital X of z. Okay, this is also very important property. So these three properties are very important. One is linearity, time shifting, and the differentiation. Okay, differentiation is z transform of n into x of n is basically equal to minus of z into d by dz of x of z. Okay, so we'll take one example on this. Suppose we are having h of n equal to n plus 1 alpha to the power n u of n. Now here we need these properties. Okay, so we write this alpha to the power n u of n. Suppose this is x of n. Okay, so this h of n is n plus 1 x of n. So this I can write n into x of n plus x of n. Correct. Here we will use two properties. One is the linearity, other is the differentiation. Okay. Now find h of z. So h of z is basically equal to z transform of n x of n plus z transform of x of n. Correct. Now First find this Z transform of n x of n. This we know from the differentiation property. Here we will use the differentiation property. Okay, so this is basically equal to minus z d by dz of x of z. Okay, so first we will find the x of z. So we know that x of n equal to alpha to the power n u of n. So x of z equal to summation from n equal to minus infinity to infinity alpha to the power n u of n z to the power minus n. So it will go from n equal to 0 to infinity alpha to the power n z minus n. So we know that this is equal to alpha z to the power minus 1 to the power n, which is equal to 1 by 1 minus alpha z inverse. Okay, here we say that the region of convergence will exist for mod of z is greater than alpha. Correct? Now we need to find, using differentiation property, we find the z transform of n x of n. Okay, which is equal to minus z d dz of x of z. Correct? Now d dz of x of z is what? Find the differentiation of this. This is equal to minus 1 divided by 1 minus alpha z inverse square. Correct? Is this correct? This u by v rule we will apply. So we will end up with multiply. We need to multiply this with minus alpha z inverse. No, this is z to the power minus 2 will come. It will come here. This is minus 1 into alpha z to the power minus 2 will come. U by v rule if we apply. Okay. Now, are you getting this thing? Any doubt in this? What we have done? We are calculating the x of z, d by dz of x of z. So this is equal to denominator square into minus of the differentiation of the denominator in the numerator. Okay. So z of nx of n, this is equal to minus z into minus alpha z to the power minus 2 divided by 1 minus alpha z inverse square. So this is equal to Z into Z to the power minus 2 will be Z to the power minus 1. Alpha is there. Divide by 1 minus alpha Z to the power minus 1 square. Okay, now we will apply the linearity property. So we will find the h of Z equal to the Z transform of this plus Z transform of this. So what is the Z transform of this? Just now we have calculated, that is alpha Z to the power minus 1, 1 minus alpha Z to the power minus 1 square, plus what is the Z transform of this x of n, which is equal to x of Z, which is 1 by 1 minus alpha Z inverse. Okay, and the ROC for this is mod Z greater than alpha. Okay, now if we simplify this term, so what we will get, we will take 1 minus alpha Z inverse common. So this is alpha Z inverse plus this numerator is 1 minus alpha Z inverse. So we will left with only what? 1 divided by 1 minus alpha Z inverse to the power this. And the ROC for this is greater than alpha. Okay, again draw the ROC Z plane, real of Z. This is entire Z plane. Okay, so if this is alpha, then we'll draw the circle here, and if Z is greater than alpha, then we'll be having the ROC like this, region of convergence. Okay, so using the properties also, we need to use properties here in this example. This type of example also you will find. Okay, in the quiz also. So by looking at the problem, you should understand which properties will need. Sometimes you also need the property of time shifting. Okay. So have you understood this example? Is it clear with you, this example? Yes, students.
I guess it's okay.
Have you
Just
understood
need
this
more practice.
calculation part?
Yeah, I guess so. Just need more practice to fully grasp the concept part.
Yes. Sorry, what you said?
It's okay, doctor. Just need more practice now.
Okay, okay. So we will stop here today. Okay. So please practice. Some examples are given in this PPT. So you can practice these examples at home. These examples. Okay. Okay, then for today we will stop here. Is there any doubt?
No, doctor. Is this slide will be shared on the model, doctor?
Yes, yes, yes. I will share it.
All right, doctor.
Okay.
Thank you, doctor.
Okay. Thank you. Okay. Have a good day. Thank you, students. Have a good day. Bye.
Bye.
Oi, Pis. Keluar. Keluar, Pis.
Halo. Allah. Turun. Minum.
Ada saya makanan nggak?
Di sini Wila bawa. Cepatlah kau, yang membuat TikTok nih.
Bah. Saya punya.
Wih, masih kena record gila anjing.